Sort of in line with a little bit with what Neil was talking about, but maybe diving a little deeper. I'm going to look at this notion of how do you get to delivering a better 5G experience, within a full stack infrastructure within a cloud native network by delivering full stack assurance. And I'll show you what a full stack assurance means in just a second. So let's start with just this idea of with as we started down this journey a while ago into a service assurance within a 5G domain, we had this notion of data as a problem, and we're getting what we call a tidal wave now of monitoring data, and Neil sort of touched on that earlier when he mentioned that there's in fact maybe too much telemetry in the network right now that to deal with, and this is one of the things we saw, and as we were speaking to some of the carriers, they were saying that it couldn't go on this way. They can't afford to monitor data the same way they used to monitor data. It's just not a tenable solution. So first off, we're going to look at in this talk how we get around that issue of too much data in the network, and then we're going to talk about the issue of the abstraction and creating a blind spot in the network. So you have this notion of abstracting the network and service layers away from the hardware, and everybody knows why we do that, and it's a great idea. It allows you to write software easier. But it does create this problem, and I think Neil maybe touched on that just a little bit at the end, of creating the blind spot between what's actually happening in the infrastructure layers and what's happening in the network and service layers above, and how are they related, even though you've abstracted them. Next thing, and again, thank you, Neil, for the segue on this one. We're actually going to talk a little bit about why a cloud native assurance solution, a cloud native network needs a cloud native assurance solution. You can't do service assurance in a cloud network without being a cloud native solution yourself, just for all the reasons he talked about in terms of scalability and growth and dynamicity of the network. And then finally, at the end of the day, the only thing the customer actually cares about is quality of experience. And that's the only thing the operating company should be caring about. And again, thank you, Neil, for just sort of touching on the fact that the only thing BT really is passionate about is the customer experience. So this is central to what we're going to look at as well. So with these points in mind, let me just go jump in and talk a little bit about the data tidal wave. So we, at EXFO, we started creating in the 5G world what we call an adaptive service assurance solution. So what does that mean? It means it's an assurance solution that can grow or shrink depending on the necessary probing or analysis that needs to happen, and it allows itself to be a little bit more cost competitive. And again, everybody's starting to understand now that operating networks in the cloud is very expensive, a proposition. So, we get this piece of data from one of our operating company partners that they expect that in a 5G world, they could be pulling as much as 40 petabytes of data per hour of monitoring telemetry. So that's a lot of monitoring data to have to deal with, and you don't want to be moving that and storing that in the network. The cost would become prohibitive. And in fact, what they said was it would be so prohibitive that they essentially, if they continued on the way they did it in 4G, they wouldn't be able to afford it. It would cost so much money that they figured they could only afford to monitor about 20% of their network. So that's a pretty big problem to have. And then, of course, what that means is that if you only monitor, if you have that much data to monitor, and you're trying to do it in an old style way of just store everything centrally and then post-process it, isolating your faults becomes even more and more, time consuming. And this is the problem that they say that their number one problem in the cloud network today is literally isolating the fault. They not even resolving the fault, but just finding which domain that fault exists in. So these are some interesting things that we learned. And so that drove us to this notion of adaptive service assurance. And by that, we mean, being able to find the right data at the right time in context of the problem that you're looking at. And how do we do that? Well, you do that by a number of ways. You can you instantiate probes and agents only where needed. So, we've obviously moved away from physical devices for probing, for gathering data. Telemetry off the network elements is key. And where we don't have adequate telemetry, we can certainly deploy containerized probes or containerized agents to round out the data. But essentially, you have to be able to scale up and scale down that aspect of the network monitoring solution just in order to focus in on the problems that you see, and then focusing and pull it back out again once you've seen it. So that comes down to this notion of only look for, only gather, only extract, and only store as much data as you need. You don't want to be storing 40 petabytes of data per hour. You only want to be able to store the data that you actually need to get at later on if you haven't resolved it in real time already. And then that's the other thing is, again, coming back to this notion of just collecting, focusing, only getting the things that you need to analyze, what's necessary right now. And it's our assumption, and we've seen sort of proof points that say that by doing it, we can reduce the assurance footprint versus 4G up to about 90%. And this is really the target that operating companies are telling us they need to get to in order to make their business cases work in a 5G world and in a highly scalable cloud world as well. So with that in mind, let's talk a little bit about the abstraction problem. So we've abstracted the network and service layers away from the infrastructure, the infrastructure, the Linux, the OpenShift world, the Kubernetes world, and this is done obviously again for very good reasons. Gives you a very scalable, highly dynamic world, and it allows people that write software in the service and network layers to not worry about what the infrastructure looks like, which infrastructure they're running on, and such. But it does mean that essentially there are now two worlds again, and we are all very well aware of some of the silo issues that exist within an operating company that prevent different teams from talking to each other, prevents the democratization of data in these worlds. So you have different teams and managing this network, and at the end of the day, they look at different things. They have different tools. They look at different metrics. They may be interested in different functionality. They have different goals. At the end of the day, what they've been tasked with by their upper management is potentially different goals that way too. So how do you deal with this? And this is creating what we call the visibility gap. This makes sense. It's when there are issues in your quality of experience, in the quality of service in the upper layers. This gap means that you have a very difficult way of deciding whether or not the problem is in those layers up above or whether they're in the infrastructure itself down below, and stitching that together to find out what the true issues are has become a problem. And to understand why that is a problem, we did some surveying, and we worked with heavy reading at the beginning of this year to run a survey. And one of the things that we found, which I thought was interesting, was about 70% of the service providers we talked to, they said, they all agree that detecting and correlating faults is more difficult in a cloud infrastructure. I don't think that's going to come as a surprise to very many people, but it's a pretty big number. And sort of, one of the ideas behind that is they said that, of those CSPs, fully 20% of them said that isolating the fault domain could take up as much as 3/4 of the time to resolve the fault. So that's an extraordinary long period of time. If you think about it, why is it still taking that long to just find the fault, not even solve the problem, but just find the fault? And as a reference point, if you go back to the 4G networks, we asked them, they said that only about 4% of the CSPs said that it would take that long in a 4G world. So clearly that's kind of highlighting that the 5G networks are just that much more complex. And that, of course, has to do with a lot of things. One is scale. They're much larger networks. They're much more complex because they are so microservices based, such a strong service based architecture to them, that they become more complex to get their head around. And people probably aren't used to dealing in that sort of domain yet. So that may be part of it. But at the end of the day, you look at it and they said, why is that? And they said they believe that they just don't have the tools yet to do it. They have tools that were made for a different world, for a different time, and they haven't yet seen the tools that allow them to do this in a very highly efficient and scalable way. And by efficient and scalable, again, what we mean is we're getting at this notion of AI and machine learning, is that you have to allow the systems to start to look after themselves. You have to allow the systems to figure out and identify the problems, to correlate the problems, to see the problems from top to bottom, from edge to core, and then get that 75% of your time in identifying the resolution, identifying the fault, to happen almost instantaneously because you have machine learning and AI that can identify it quickly. So what did we say? So this is what drove us to our next step. And this is where we started to work with a little bit more closely with Intel on this one. And we said, well, how can we bring these services back together again? How can we close that gap so that the network and service layer is, while it's abstracted from a software sense, it's not abstracted from an operations sense. So we said, okay, well, first off, we have to deal with the data problem. We have that 40 petabytes of data being generated in the network. How do we get around that? So the idea is now you need to start doing anomaly detection at the edge of the network. You have to do anomaly detection where the anomalies occur. You can't force all the data into the core of the network and manage it there. So that's the first thing. So by doing that at the edge, we can reduce the amount of data being pushed through the network. And of course, transporting data and storing data in the network is also a very expensive proposition for most carriers. So this, we think, is one of the very first things that we had to do to get around that issue. And when you do that, the other thing is, in order to bring these things together so that you can make sense of them, so you can correlate them, you have to contextualize the data. And by contextualizing it, I mean, you have to add that basic idea of timestamps, consistent timestamps, but you also have to factor in adding metadata to talk about the location, the Kubernetes environment that it might be in, the physical servers they're running on. All this sort of information needs to be contextualized so that when you get it and you bring it into a centralized location, you can now do cross-domain correlation. Now you have a set of data that sits across all domains that's been contextualized into a common view. So now your network teams, your service teams, the cloud and the IT teams, they all have the same view of the world. They can all see the same data, so they can see that when there's an issue in the network layer or a service layer, and they can look into the infrastructure layer, they can see things that have happened in the infrastructure layer that align, that correlate with each other strongly, and they can go start to investigate those very easily. And this, of course, because it's all done, we're using machine learning and artificial intelligence, these things can happen automatically. And by happening automatically now, you give them a new set of tools. You give them a common screen, right? A single pane of glass that all these teams could use to do operational analytics, to do service level agreement management, service quality metrics, and of course, root cause analysis. Most importantly, be able to do root cause analysis very quickly and automatically. And of course, as a result of that, you can drive your automation engines, your back office systems, as well as the orchestration platforms, and you drive them with a complete view from physical infrastructure, from CPU to quality of experience, all the way from the edge to the core. So this is what we're calling full stack assurance, and this is what we announced just last month or earlier this month as now available for trials, and will become generally available in the fall as a feature on our adaptive service assurance platform, cloud-based assurance platform. And we believe that this is the sort of information that you need to give you the actionable insights to deliver that better 5G experience. Because at the end of the day, the only thing that actually matters is the customer's quality of experience. And the only way you can positively impact the customer's quality of experience is if you can see it, you can detect it in real time, and you can then act on it in real time as well, without having to do 75% of your time finding the problem. So how do we actually do this? I think this is more an interesting part of it. So again, I said we partnered up and partnered in a loose sense. We cooperated well with Intel to work on their telemetry interface, something that they call their platform telemetry insights, and we allowed them to feed that data now into our SenseAI analytics engine, our correlation analytics engine, and so we have a couple of servers from Intel that run basically an open free 5G core, and within there we're running some cloud services, and we simulate loads on it, and we simulate faults within here, and then we can see what happens through using active testing today. But of course, it doesn't have to be an active test. It could be any sort of test that you need to correlate and pull that together. So we got this working in collaboration with Intel, and so now what we have is a function or a lab environment that looks like this. So now we have this 5G core running, and we have one of our probes basically doing UE registration on a constant basis. So it's just continually trying to register as a UE on the network, and it's measuring the latency of the response time. So it's measuring the functionality of the 5G network, and we have a free 5G network running on these servers, and we've pinned certain functions to certain CPUs so that we can isolate the effects of that. And then what we do is we have a program called StressNG, and StressNG can go in and stress certain CPUs within the server itself. So basically, max out the CPU within the multiple CPU cores that are on the platform, and we look at various metrics coming off of there as well. So in fact, in total, we're looking at about 1,600 metrics total, and we run this in such a way that we stress the system out every 10 minutes just to see what happens. And one of the things we'll do is we'll cycle through the different CPUs that are available. So by looking at it, you can see that every 10 minutes, you can see there's a stress happening, and there's a fairly well-defined correlation happening. So when we stress the same CPU, so we picked on the NRF, if you will, for that function, and when we stress the same CPU that the NRF is running in, you can see that there's a fairly strong correlation between what latency is and then the loading of the CPU. Now we also did it in the sibling, so these are hyper-threaded CPUs. So by using the sibling CPU to the one that the NRF is running in, and the sibling CPU just essentially is a second CPU, but it shares certain resources within the device. You can see there's also a strong correlation. And interestingly enough, then when we stress a third CPU at 10 minutes later, that's just a CPU, an unused CPU in the socket, but not related to the NRF CPU. The impact, obviously, as you would expect, wouldn't be as strong. And this is what Intel would call a noisy neighbor problem. This allows you to start to identify problems, and you can see obviously what a strong valuable piece of this is that you could look at this and you can say, when I'm having issues in my 5G services, and suddenly latency of some function goes up or some part of the quality experience degrades, you may not, if you weren't able to see into the bare metal layers of the CPU at the time, you may not notice that in fact you're in a multi-tenanted MEC domain, and some other process from some other customer potentially is for some reason stealing CPU cycles or maybe taking too much memory or something. So you start to see these subtle little problems that weren't necessarily visible by just looking at quality of experience and quality of service metrics in the cloud layers. So this is kind of what we saw. And of course, interestingly enough, we see other things showing up in here. If you're wondering what the other little blips are, those are typically some of the other processes that are running in the servers right now, just to run the setup. So just different sort of administrative functions happening there. So we thought this was quite an interesting exercise, and the advanced machine learning algorithm that we have now running within our analytics platform is what's being shown in the dotted line, and it's being able to predict. Essentially, it's not doing forward prediction because obviously these are very random events that are happening within here, but it's being able to predict that when latency jumps up, it can look and see very quickly that what the root cause issues are of that latency increase of the metric that you're looking at. So it's really the machine learning is really being used to do root cause analysis, and it allows you to very quickly identify now that you have issues within your service layer because of the following issues in the infrastructure layer. So this is kind of an interesting aspect, and just to touch on one last aspect that we're going to start working on, if we think about the platform telemetry coming back in here, and again, Neil touched on this a little bit earlier too about power being an issue. One of the metrics that we'll be able to get out of this platform as well is the power utilization of actually every individual CPU within the server. So now we can start to monitor power on a per server per CPU level within there, which of course in a MEC environment is a very critical aspect, because it says that you are in a very resource constrained environment. So to be able to see within the infrastructure itself and monitor the utilization of every processor within the MEC, but also with with all the memory within the MEC, but also how much power is being drawn. And if you need to, you can slow down certain processors save power, or you can even start to consider moving workloads back into a core that maybe don't need the real-time nature of the mech. Then there are certain ways that you can look at it. So we believe that this sizing and power management will become much more prevalent, especially as companies as well are being start to see the impact of green policy and green regulations coming in, and the ability to audit their power consumption and comply. So with that in mind, I think I'm pretty well wrapped up, but I'll just go back and sort of summarize. We've seen what adaptive service assurance is, and we've seen that it's going to allow you to keep pace with this tidal wave of data, this onslaught of data coming in that needs to be dealt with. We've seen that basically by moving into a cloud environment, by going along down the lines of containerization and open APIs, that you can get to fault correlation with machine learning and remove the blind spots that are showing up in there. And this container-based network is in fact highly scalable and gives you a very scalable distributed solution that can grow and shrink both as the network expands horizontally, to deal with loading, or just as the network grows, and then or as issues show up as well. And then we have this notion of bare metal to application and core to edge visibility, and that's what's going to allow you to derive a better 5G experience for your customers. And Annie, that's essentially it.
Well, thank you. I do see what you mean about Neil was a really great panel to have right before you, even if that was incidental rather than planned. So we do have a question for you, please, Ken, from Madad. And he says, or she says, I'm sorry, I don't know which, my ignorance, can a security attack be initiated by using the noisy neighbor phenomenon? And how is this dealt with?
That's an interesting question that I honestly haven't really considered, but just quickly thinking about it, I think the answer would be yes. I think, especially as I said, especially in a mobile edge compute environment where you are, resource constrained. I can see that if somebody is able to get in and put applications in the server that could then take over CPUs and effectively run what we were doing, a stress NG function in CPUs, you could certainly impact the quality of experience. I don't think you could do a complete denial of service that way, but you could certainly impact quality of service. You could certainly impact quality of experience for a customer by doing that. So how would it be dealt with? Well, I think the way you deal with it is exactly what I kind of touched on at the end. It's the ability to see the performance of every CPU, to see the utilization, and then to be able to see which you can look at. Actually, now we'll look at the details that come from the contextualized information. Gives us the notion of the workload, the pod, the container, the physical device, the CPUs it's pinned to or not pinned to. So we can see the complete environment that workloads are running in, the workloads that are stealing, for example, CPU cycles. So we can identify what and who they are and shut them down. I guess that way would be my answer to that one. But again, I haven't really jumped into that one too deeply.
I also think it's interesting when we think of clouds, you think of big amorphous, fluffy things, and yet really key parts of your presentation and also Neil's has been about right down to the CPU level and running capacity and workload. And so it seems to me to run cloud successfully, the management of it needs to be granular.
Very true. That's to me, I think that was always the myth of the cloud network, was that people forget that the cloud still needs a network to run on. A cloud needs a physical network. It may be viewed as this, like you say, this fluffy, nebulous thing that's there, enveloping everybody and allowing everybody to talk. But in fact, it still runs on a physical network. It still needs hardware servers. It still needs optical cables connecting. It still needs wireless networks connecting them. And so you can't ignore the fact that it's running on hardware. And again, in the large data centers where you can look at those as having infinite CPUs, infinite GPU, infinite memory, infinite power. Just move things around. If there's a problem, shut that server down, move it over, move everything around, orchestrate around it. Everything's fine. But in a constrained edged environment, you don't have that luxury. You have a finite, very tightly resource constrained environment that you have to manage very carefully if you are going to continue to meet the quality of experience promised to your customers.
Interesting. I love it. We come up with one solution, but the new solutions always bring new issues.
Yeah, the problems never go away. They just get moved to a different place.
Ken, thank you so much. That was really very educational for me, at least, and I'm sure for many other people. Thank you very much indeed.
Thank you so much for the opportunity to be here. Thank you.